Here we have a circle written in a different way. Find the center and radius of the circle x squared plus y squared minus 8x plus 6y minus 3 equals to 0. This form of writing the equation is what your textbook calls the general form of the circle. And you see this crop up if you take more math, then eventually you confront the most general form of a quadratic equation in two variables would be ax squared plus bxy plus cy squared plus dx plus ey plus f equals to 0. So that's the general form for a quadratic equation using x's and y's. We have a second degree terms here and here, but this term is also second degree because the exponents are 1. When you add those exponents together, you get degree 2. First degree terms, here's a constant. All right, now when this term is missing and when a and c are equal to each other, then this equation would represent a circle. And when a and c are the same sign but different numbers, and how that translate up here, for example, suppose I had 2x squared plus 3y squared. You know, if they have different coefficients, then usually that's an ellipse. If there was a minus in between here, then it would probably be a hyperbola shape. And if either x or y was missing, and there was no xy term, then it would be a parabola. And so we have circles, ellipses, hyperbolas, parabolas. There are actually 3 other forms you can get from this equation. All 7 of those forms are called conic sections. And conic sections were explored in ancient Greece. That fascinated them. In fact, there's a book still in print on conic sections written by Apollonius, who lived in ancient Greek times. And you could find that probably in a lot of university libraries. I know Wright State has a copy because I checked it out once. And so, anyway, the conic sections are, and I'll just kind of do this quickly. Do you know what a cone is? Possibly not. You know, most people think of cones as like ice cream cones. Well, a true cone is what you get if you take a line, fix a point, and then rotate it in some way. If I rotate it in a circle, then I create what's called a right circular cone. And so a right circular cone is sort of like 2 ice cream cones, end to end, but going off to infinity in both directions. And so this is a true cone. Well, the ancient Greeks were fascinated by this geometric shape, and they started wondering, well, what do you get when you slice it in different ways? And depending on how you cut it, you get one of those 7 shapes. 4 of them are called the traditional conic sections: circles, ellipses, hyperbolas, parabolas. And then the 3 degenerate conics. One is 2 lines intersecting, one is just a straight line, and one is a point. All right, so I'm not going to worry about all that stuff. But this equation shows up if you take more math, you'll run into it. We like to study this in Calculus 3 here. And in particular, this term here is what gives trouble, because when you have an xy term, that means the shape has been rotated into plane somehow. And figuring out that rotation is really makes things unbelievably complicated. So that's why it's we don't deal with this term until Calculus 3 at this college. When it's missing, then it's a little easier to work with. But if this term was missing, and if a and c were equal coefficients, you would have a circle. And this fits that form. All right, so anyway, I wanted to give you a little bit of background on the where a lot of this stuff comes from. And so now you see where these kinds of equations come from. That is a special form of the general form of a quadratic. Well, it's called the general form of a circle that this is written in, and I really don't like it. I will never ask you to write an answer using the general form of a circle. Because if you have the information to a circle, when you convert it to an equation in this form, you lose that information as far as easily recognizing it. Because you can look at this and what is the center of the circle? What is the radius? With a little practice, you could probably figure out the center by eyesight, but the radius, that's a tough one. So, all right, well, nevertheless, this kind of problem shows up in every college algebra book there is, every course, and so it's a traditional topic, and it's a good math topic. In order to identify center and radius, I have to figure out how to manipulate this equation into the standard form, the x minus h squared plus y minus k squared equals r squared form. So if I can convert this into that other form of the equation, then we can immediately recognize the center and radius from it. Well, the process of doing that uses completing the square. You might recall completing the square in the last chapter is what is used to solve quadratic equations, to find the quadratic formula. So we're going to use a very similar process here.